We added LENR-CANR.org also works. There are seminal LENR papers that are appearing at this new website. The new name for cold fusion is low energy nuclear reactions because it's much more general phenomena than was initially believed. And another thing is the 10th International Conference on Cold Fusion, ICCF 10, has a website, which is www.icc place in Cambridge, the last week of August 2003. Peter Hagelstein right over here is the chairman of this conference. I'm the technical chair. And we, just about to start accepting abstracts for that. And on this website, you'll be able to find out how to do that. You can find a lot of interesting stuff here. And you will be hearing about this website, and there will be more information about that. My name is now just about 11:15, so I'm going to start this session. My name is Scott Chubb. I'm from the Naval Research Laboratory. The rules are, each talk lasts for 10 minutes, then 2 minutes of questions. One other announcement. At the end of what's on this scheduled program, if people want to stay around, I have an additional paper that I've requested to be placed in this session, but it couldn't be placed in the session because it was a post-deadline paper. I presented it as a poster on Wednesday, and if people would like to hear that talk, we could go through it. It's an interesting one. It's from the Italian group on cold fusion. Anyhow, as I was saying, each talk is 10 minutes long. At 8 minutes, I'm going to ring a bell. At 10 minutes, I'm going to ask you to stop, and at 12 minutes, I'll yank you off. It's intended that you have 2 minutes. There'll be 2 minutes of questions. Okay. So, the first speaker is Dr. Chubb, who used to work for many years at the Naval Research Laboratory. He's now retired and has been conducting low-energy nuclear reactions experiments. The title of his talk is Optical Lattice Bose-Einstein Condensates and the DD Fusion-Iwamura Connection. Dr. Chubb.
Well, my talk is really about ion band state theory, but I think that other branches of physics may be able to give us some guidance as to how one can create conditions that allow ion band state theory to apply. So first, let's look at what the ion band state theory is. You can read this. It says basically that
push on it.
That cold fusion requires a coherent many-body deuteron system which exists within an external potential containing n-cell potential wells where n-cell exceeds a critical number, n-cell critical, which is probably of the order of 1,000 to 10,000 based on an actually energy minimization calculation. The many-body deuteron system is a superfluid. It's characterized by having a small fraction of each deuteron of a many-deuteron subsystem, many-body deuteron system, of each deuteron's charge in any one unit cell. So it's not like normal chemistry. And for a nuclear fusion to occur, this many-body system must be embedded in an external environment to which energy can be transferred. For direct heating of the environment, as opposed to just putting it in kinetic motion, at non-zero temperature, the energy transfer involves, in my opinion, multiple electron scatterings, which in their sum receive the nuclear energy made available. So that's the framework with which causes me to look at other branches of physics, and in particular, the very active field these days, which is atoms and optical lattices on Bose-Einstein condensates. And one of the important papers of this was published a few years by Jacks et al. And this figure, in this kind of condition, a Bose-Einstein condensate, a many-body atom system, in this case sodium atoms, are confined in potential wells that are produced by a standing wave pattern created by laser light. And in a potential well, any one potential well, the mass distribution portion of the particle in there is calcium, basically. And what this theory, Jackson all did, was they studied how the many-body system in this optical lattice varied with the depth of the potential well. This is a theoretical study, but it has been reproduced experimentally, which we'll talk about in a second. But what this data, this figure shows a plot which shows how, first thing, the so-called hopping function varies with the depth of the potential well in units of heat recoil energy. This is high hopping rate, this is low hopping rate. And the point is, when you have the high hopping rate, the theory says you're in a superfluid condition where you have fractional occupations of each unit cell. If you have deep potential wells, you only get integer occupations of each potential well. So it seems to me that speaks a little bit to our situation where we want to have ion band states with a fractional occupation of each potential well. Okay, if you have the rapid tunneling with repulsive atom-atom interactions, the Bose-Einstein condensates remains in a partitioned atom superfluid, a fractional occupation of each potential well. If the potential wells become deep and you can turn them up, make them deep by turning up the laser intensity, an incoherent phase with integer occupations separates out from this superfluid, it's called a non-insulator, and it steals the atom from the superfluid, and in this new phase, there's a constancy of number in each potential well, which replaces a constancy in the being able to define the wave function phase of the superfluid in each potential well. Now that transition has actually been observed experimentally, and by Greener et al. So the question is, can this kind of system where you have theory concerning neutral atoms and lasers, very low temperature, can any of that spill over to our situation where we're dealing with hydrogen and metal physics? And I think it has some lessons that maybe we can learn from. But we have to keep in mind the very different situations which we have in these lattices, for example. With the optical lattice, the lattice is not affected by whether you have an atom in that populating that set of potential wells or whether you don't. There's no self-trapping. There's nothing that can disturb the periodic order created by the laser. And if you have a many-body superfluid, you have a coherent lattice, which means that if you try to do an energy minimization calculation, you move one atom relative to the boundaries of the potential well with which it is. All the atoms move together. They're coherently linked, and so you essentially are moving a hydrogen lattice relative to, well, in this case, you're moving a sodium atom lattice relative to a standing wave pattern created by the laser. Now, typically, in normal hydrogen and metals, palladium 0.1 palladium hydride 0.1, for example, you perturb the periodic symmetry because you have self-trapping going on. To accommodate the electron that provides the neutralization of the hydrogen ion, it distorts the lattice locally, and you destroy, to some extent, the periodic symmetry of the system. So you locally expand all of the lattice, you locally alter the electron density distribution, and maybe the way they're aligned configuration. And you distribute the density of the particles within a single occupied unit cell. But the case for when you're dealing with a many-body system, an ion band state system, you have a no self-trapping situation. You are depending upon the symmetry being preserved. You use block functions to represent your equations. You have no self-trapping, and if you're doing an energy minimization calculation, you can dilate the lattice, expand it, but you still maintain a 1/n cell fraction of the ion density within each unit cell. And this kind of a calculation is similar, that doesn't disturb the lattice symmetry. In fact, the medium theory calculations like used by Pushka and Niemann and Astaldi for surface states of hydrogen are of this no self-trapping type. And I just want to mention one thing, that I think when you really talk about metal hydrides, I apologize for this thing not being right, but you really need to take account of what atoms, where atoms are, and whether they're in a self-trapping situation or a non-self-trapping situation. The band state ions are non-self-trapping situation. So it's possible that in the Hines and Parsons situation where you have 8/10 D to DD ratio or higher, that the band state ions are only maybe 1/100th of or 1,000th of an ion in any one potential well. But we don't know necessarily where those are. They could be in the octahedral sites where the normal non-self-trapping ions are, but they could be in the tetrahedral sites. And I think if you consider the Iwamura experiment, it's very possible where you have much lower concentrations, that these ions are going into tetrahedral sites, and that they get there because of the diffusion process, which he uses, where he has diffusion barriers which are overcome within the metal. And this sort of thing will then spread out over the whole crystal and can interact with surface atoms, which is what his observations are concerned with.
You done?
Yeah, not really.
Okay, I mean, we have time for maybe one question.
Tom, there's a literature on the hopping process in palladium hydride, which you're undoubtedly familiar with.
Yeah, the footpack, for example.
In the bulk palladium hydride, at low temperature, under liquid nitrogen temperature, the coherent process you're talking about dominates the site-to-site.
Well, that's very interesting, because Pukai doesn't really discuss the low temperature situation.
That's my basic conclusion.
There are many other authors. I can send you some references on it. Above 100 degrees Kelvin, the transport is completely phonon dominated versus like other site hopping interactions.
That's in the phases that are well known, but above 0.7 is not known. That doesn't exist. Above 0.7. And what you said here in this last structure, and principally you're saying it's ordered, so this is really a supercell. Is that what you're saying?
No, I'm not saying that's not a supercell.
Well, how is it ordered?
No, this is not necessarily ordered.
Oh, okay.
That's not ordered.
Well,
This is ordered.
Are there band states here? How can it be?
There are no band states in this, only in this.
Well, how do those form if the thing isn't ordered? Well, anyhow, that's all right.
Well, if they're in the tetrahedral sites, they have to be ordered.
Fine. I don't know. I'll talk to you about it. Okay, it's time to call for the next question, the next speaker. Let's thank our speaker. The next speaker, mind it. The next paper is by Roger Stringham. This is an easy one. I just turn on the videotape.
The microphone on?
Oh yes, it's a microphone.
Oh, there's another two.
Okay, put that on.
I got more problems there.
Sorry.
Anyway, I'd like to see, is this working? Hello? Something's happening.
Is this just for the video, or is this for the...
No, it's supposed to,
No, it's supposed to be for the room.
Can I talk louder? Can I work all right?
I'll work.
I mean, I'm using up my time here.
No, you're not.
No, you're not.
I'm giving you a start, I'm giving you a start.
Okay. Anyway, I would like to suggest the reason why cold fusion has been so difficult to explain and so difficult to reproduce is because an incorrect assumption has been made. And I'd like to suggest that this incorrect assumption has to do with where the nuclear reactions are occurring. That is, the nuclear active environment. And that environment has assumed to be beta palladium deuteride. And I would like to suggest that this is wrong. If I have a pointer here, push on. This paper is in full text on this website, www.lenrcanr.org. So anybody that's interested can look it up. And I will tell you some more about this website at the end of the talk. But what is the nuclear active environment? The nuclear active environment is the unique place in a material where anomalous nuclear reactions occur. Only this environment allows them to occur, and this environment is significantly different from normal material. So it's very important to analyze, to understand the nature of this environment before one goes about trying to explain it. Where is the nuclear environment located? I would like to focus on the Pons-Fleischmann method, and that method involves electrolyzing a piece of palladium in a LiOD electrolyte and loading the palladium with deuterium. The process also rains down on the surface a wide collection of other impurities, which I think are important. Now we believe, most people I think here in the field believe that the nuclear active environment is in the surface of the material. Most people except Scott. In any case, I would like to remind those of you who believe this and perhaps convince Scott that it is in the surface. And this is based upon the fact that there's almost a complete loss of helium to the gas. Any helium, this reaction, the nuclear reaction, does produce helium. That's been demonstrated a number of times very well. Any helium that's produced in bulk material cannot leave. That's also known. So this helium must have resulted from a reaction very near the surface. The appearance of tritium gas in the electrolyte rather than the evolving gas. We know now that tritium that is in the electrode is displaced by deuterium and goes into the gas, whereas when it's generated in a cold fusion cell, it's found in the electrolyte, thus proving that it had to occur very near the surface. The observed heat is generated on the surface. This is seen by infrared camera studies where hotspots are located. Transmutation products are located only in the surface region. The presence of melted regions are seen on the surface. And the ability to generate large effects using thin films on an inert substrate. If it were in the bulk, which has a large quantity of material, and then you tried to make it happen in a few microns of material, you would expect a corresponding reduction in the amount of heat production. That's not seen. The heat production is comparable. All right, well, what is the surface composition? What's it consist of? Well, first of all, the deuterium to palladium ratio is greater than 1.5 and perhaps as high as 2. And we'll talk about that in a little bit. I'll go back to that. The surface is mostly lithium, platinum, and other impurities, with a minor constituent of palladium. The surface is frequently covered by nano-sized particles. Those are the characteristics of the surface that are now known to be true. So let's go back to the first one. The surface composition is difficult to measure, and the numbers that you see quoted are the average composition, not the surface. The surface has obviously a much higher composition than the average. This is one study of the surface as a function of depth. You can see there was a certain amount of surface deloading here, but the composition is high as 1.7. There's another study using morphin oxygen to measure the amount of deuterium that went into palladium thin films, 2 microns on platinum. It's a function of the current density, but you see it's at least as high as 1.5, and perhaps higher than that, since those samples were not nuclear active, and therefore presumably didn't have as high a composition as required. Well, people would argue that this extra deuterium, which otherwise cannot go into the octahedral sites of the face-centered cubic beta palladium deuteride, go into the tetrahedral sites. A lot of studies have been done to try to determine whether or not that's true under equilibrium conditions, and all have failed to see tetrahedral deuterium. On the other hand, there's another possibility. There are other compounds or other elements that produce hydrides, one of which is zirconium, that forms a hydride similar to the one that palladium forms, the beta palladium deuteride, but it also forms a zirconium hydrogen 2, which is a face-centered tetragonal structure in which tetrahedral occupancy is present. And I'm suggesting that the material that in which the nuclear reactions are occurring is perhaps based upon this material, not on this material. Now, in addition to that, of course, we have all of these other materials in there, the lithium, the platinum, and everything else that's been in the cell that is diffused into this thin layer. So what we have, in fact, is a very complex alloy of a much higher composition than people have assumed. So the conclusions that I would like to suggest to you: pure palladium deuteride, regardless of its deuterium content, is not the environment in which an LENR occurs during the constellation effect. The complex alloy in which the effect occurs apparently requires a very high deuterium content. On the other hand, nearly pure beta palladium deuteride appears to be active at relatively low deuterium contents, and this is using a different technique. LENR requires nanosized particles that consist of complex materials. And lastly, most theories, mechanisms, and explanations are inadequate because they have not taken these observations into account. Let me tell you just a little bit about the website.
Yeah.
Okay.
Upside down.
Not that way.
Looks like maybe. Upside down. That's the website I mentioned.
Yeah, okay, there we go. Jim Rothwell and I created this website in October of last year, and it contains over 3,000 references having to do with cold fusion, which can be downloaded and searched. It also contains, at the present time, about 165 full-text papers, mainly from conferences which are otherwise not available. This shows you the download rate of these full-text papers as a function of time. Right now, we have almost 38,000 of these that have been downloaded. So this has been a continual and increasing source of information about the field, and I would recommend all of you in cold fusion to submit papers to this website so that they can get distributed throughout the world.
What is it? Editors at LENR.org, right?
Yeah.
Editors at LENR.org.
Yeah.
I just want to make a comment. I actually, I agree with you that pure palladium deuterium, that's in quotes not where the reaction occurs, but the wave functions there can make it occur, and so it's intimately part of the system. The reaction site where the heat will be released is unbounded, or it's what I think. But, so I'm not completely disagreeing with you, but I also think that it's not just one nuclear active state that, to make body physics probably complicated as the reality. Yeah.
You showed the zirconium chart. What is your experience in zirconium? Have you done any excess heat measurement with zirconium?
No, I have not. The problem with zirconium is that when you hydrate it, it breaks up.
Yeah.
It doesn't retain a coherent structure. Right. It's like titanium in that sense.
These are very complicated systems, yeah.
I just wanted to say that the helium going into the gas doesn't mean it's the surface. It just means it's near the surface, because we know from the work of Farkas that hydrogen leaves palladium in electrolytic cells by microcracks, and that's really because it goes directly from metal to gas, is why you get the isotopic change that's produced by putting stuff in and then take
Okay.
it out. It's not, nothing about it as a person.
Let's let Peter have a chance.
Well, let me answer that.
Oh, I'm sorry.
There have been some studies by injecting helium-3 by decay of tritium into palladium. And when the helium is injected that way throughout the material, they have studied the loss rate, and of course there'd be the same kind of cracks and everything in those samples as well. The helium is trapped. The only helium that gets off is within a couple of microns of the surface.
Now, it's probably chopped in a different way than it is and comes out.
Well, you have to assume that you have a special
I'm going to have to throw
Yeah.
this.
I just don't think this is...
Is it quick?
Yeah.
Okay, go ahead.
Okay, I'm in agreement with you that it's surface stuff. I was wondering if I could twist your arm to expand upon the tritium going into gas versus electrolyte. How does that work?
The way in which the tritium enters the electrolyte is by exchange with the deuterium ions, and that can only happen at the surface. If it's trapped inside, it forms a molecule which then is inert to the electrolyte and goes off.
Hey, you guys can talk about this.
Okay.
I'm sorry. It's by Dr. Melvin Miles, who's now at the Department of Chemistry, Bates College, Lewiston, Maine. He formerly was at the Naval Air Warfare Center, where there also is an important Navy report that documented a decade of work. Melvin and I were both involved with this, and that's available on the web. It's, I don't remember the website, it's through, you can look for it, SPAWAR, S-P-A-W-A-R, and look for our names, I'm sure you can find it. Where's the important? Oh, yeah. Right there. Okay. How to use it. Next. Oh, this way. Push down on this button. Okay. Sorry, I can't get the mic working here. Both getting old, we can't see very well.
Put the glasses on.
Yeah, pretty bad eyes.
Okay, this is work I actually did in Japan. I'll try to speak loud so I don't need a microphone. Fluidized bed experiment using platinum and palladium particles. I think everybody agrees that we can measure the energy of fusion reaction just by looking at the change in masses. In fact, I have my students do this at Base College. The change in mass, you can calculate the energy in electron volts for any of these reactions. This is the reaction at the top one is what we think happens in cold fusion, DD fusion going to helium-4. There's evidence for this. We have measured helium that's equal to the measured excess power that we get. And I know in hot fusion, the energy goes out as a gamma and is lost to the cell. But in cold fusion, apparently, it stays in the cell and turns up at excess power. There's a number of theories that explains how this takes place. I also had my class calculate this. It's very important as a future energy source that we can find a way to do fusion, either hot fusion or cold fusion. If you do a calculation of the number of deuterium atoms in just 1 liter ordinary water, you can do the calculation here and you get the number of atoms, 1.03 times 10 to the 22nd deuterium atoms. There's 1 deuterium atom for every 6,410 hydrogen atoms, so that's the number of deuterium atoms in 1 liter of water. The fusion energy you could get from that 1 liter of water then is this calculation, and is 1.989 times 10 to the 10th joules. That's equal to 27,000 plus moles of methanol, or over 1,000 liters of methanol of energy, combustion energy, comes from that 1 liter of ordinary water. And the cost of extracting it would be about 17 cents, which is pretty small when you consider, you calculate that from the cost of heavy water. In textbooks I've read, scientists estimate that deuterium in any of the Great Lakes in the United States, the top 2 inches of water could provide the fusion energy equal to combustion energy of all the world's oil reserves. So I think in the future, of course, fusion of some kind has to be the answer to our energy source, eventually, somehow. Now, this is a cell we developed at China Lake in California, where I worked for the Navy. the electrochemical cell. I can't go into a lot of details. That's the palladium cathode and the anode, and we have a few misters in the cell, and we can calculate calorimetrically, which is a well-known technique in physical chemistry, been around a long time, whether or not excess heat is present. Now, to modify for a fluidized bed, I wanted to use some very small platinum or palladium particles, and I hope to get them small enough they'd be suspended in the water. Actually, the ones I got were a little bit too large. This is their size, and they weren't exactly suspended the way I would like. If they were suspended, you would need a screen to kind of hold them in this part of the cell. So you'd have ionic conduction up here and electronic conduction down through here. But they more or less settled in the bottom of the cell, and therefore they pretty well stayed in one place. But during electrolysis, the gas evolution, they did move around somewhat. But it's mostly the surface that got involved in the reaction. The particles on the surface, they were jostled around by the gas evolution reaction. So there were dynamic conditions, continuous movement of the particles due to the gas evolution coming off the deuterium gas. And the cell size is filled with 18 cubic centimeters of heavy water with lithium deuterated hydroxide. These are the calorimetric cell constants in calibrating the cell. The cell constants for the platinum particles and the palladium particles, and this is how the cell constants vary with the volume, because of course air is a better insulator than water, so it would vary with the volume. As the volume level dropped, the cell constants would change. But when they were filled to where they're supposed to be filled, these were the cell constants of the two cells, just from calorimetric measurements. Now, besides doing constant current electrolysis, we did pulse electrolysis, where we applied a pulse for 1 microsecond, and this shows the voltage trace in blue and the current trace in red, and this is times 10 to the 10, so we got up almost to 9 amps in current in that pulse, and the voltage is over here. The voltage is peak voltage was close to 100 volts, about 98 volts, and this is over a 1 microsecond time scale, very short pulse. The repetition rate, we varied it, but typically it was about 5 kilohertz, the repetition rate. So most of the time the current was off, but for 1 microsecond, and this was repeated 5,000 times a second, and it was pretty much the same trace. Every repetition we had on the screen, pretty much the same trace every pulse. So it's just a steady image, pretty much. This shows some of the conditions which I just mentioned. The peak voltage was 98 volts. The peak current, I guess that was 6. The scale, if you read off the scale, it was 6 amps where the current was. The pulse width was microsecond. The frequency, in this particular case, was 5 times 10 to the 3rd hertz. You had to calculate the cell input power in order to see if there's any excess power. This way we calculated that, and we had to figure out a little bit how to do that, but basically all the pulses were the same, so you would just take the peak voltage. You had to kind of integrate over the whole curve. Take any peak voltage, you subtract 1.53 volts, which is due to the delta H value of water, and then you multiply that by the peak current corresponding to that. So you had to do it sort of point by point, or integrate this whole curve to get that, where you subtract the 1.53 from the peak voltage for a given point, subtract, and then multiply that by the peak current. And that's the equation I just showed you. The equation right here, for how we calculated the average power input, just summing over the voltage minus 1.52 times the current, and times the time, delta TI, and then times the frequency, and that would give you the average power. The average electrolysis current, since the current was off, a good part of the time was about 12 milliamps. So the volume does not change very fast, because on the average the current is fairly small, just 12 milliamps.
2 minutes.
Okay. This shows the effect with platinum particles. The red is the power out, and the other is the power in. This was direct current, and then we switched to pulse current. So this was, most of the experiment was this regular direct current, and this is pulse current. We can see within experimental error the power in, the power out are pretty close to the same as you look at that. Now, if you go to the palladium particle, everything the same except now palladium instead of platinum. You can actually see there is more power. The red is the power output, and the green is the power input. There is definitely more power coming out than you put in, and especially when you go to pulse power, there's definitely a big difference. Well, at least you can see it experimentally, the difference in power out and power in when you go to pulse power. And this is about a 10% effect, about 10% more power coming out than what you put in. But you can experimentally see the difference there between the platinum and the palladium. In discussion summary, no excess power when we use the platinum particles, exactly the same experiment, the same size of particles, platinum, no excess power. We go to using palladium particles and we do get excess power, 90 milliwatts for the direct current electrolysis and up to about 250 milliwatts for the pulse electrolysis where you have more dynamic conditions. The tiny medical particles approximate a fluidized bed. They do move around, they're always changing. We have a rather large effective surface area. We have these dynamic conditions that people believe are important for the cold fusion effect. And because we have so many particles, we're not dependent on the metallurgical properties of one sample of metal. We have many, many tiny samples, and you're more likely to get an excess heat effect. Because we find many cases using solid samples, one metal will not work, palladium, and other samples will work. And here we sort of get around that major problem. Okay, thank you.
Okay.
Mel, why was your voltage so high? Was your molality of your electrolyte low?
What was this?
The voltage so high.
Oh, because of this peak. You're applying for a very short time period, a microsecond, you're applying a high voltage to the cell. So you do get a much higher current. This is due to this pulse. That's a characteristic of pulse electrolysis. It's not constant current. It's just for 1 microsecond you apply this high voltage to the cell, and then the cell is off until the next pulse comes around.
But is it resistant to drop in your electrolyte?
No. That would be a big part of it, because you get fairly high currents through that pulse, and so a lot of that would be the IR effect. That's what you're thinking, right?
Ed, what's the size of your particles?
We had that up there, if I can find it.
It's 600 millimeters. 600 microns.
Yeah.
600 microns.
600 microns?
Yeah. They were so small, they just looked like those specks with your eye, but if you looked under a microscope, you can see they're just tiny, a very, very tiny diameter wire that was just chopped. They were cylindrical pieces when you looked under a microscope. But just looking at them with your eye, you couldn't hardly tell that.
But they were more or less the same size.
Yeah, very close. They're all the same size, pretty uniform, right?
Okay, that's it. Oh, well, go ahead.
How did you make those particles? Was it like palladium ink, or what did you use?
Before, this was done in Japan. I was a guest researcher there in Japan, and before I went there, I told them I would like to try this, and so they ordered it for me, and they were there when I arrived.
Okay.
But I think I got them to knock the metals in Japan. Okay.
That's fine.
used for ink.
Okay, no,
Yeah, perhaps, right.
I'm sorry, I gotta stop. The next speaker is, from Austin, is Dennis Letts, and the title of Dennis Letts' talk is Laser-Initiated Heat Release from Electrolytic Systems.
Good morning. I am Dennis Letts. I live here in Austin, USA, and this is my 11th year of full-time experimentation with this particular process. Not with lasers, but with other things we considered. This particular cell was active yesterday. One of the benefits of full-time experimentation is you can have pretty current data. Yesterday this cell was producing excess power, apparent excess power, witnessed by several guys in this room. We shut it down last night and brought it in for show and tell. It looks pretty much like the drawing, hopefully. And I'm going to pass it around the room, particularly to the younger folks back there that maybe haven't seen this thing. Can you give us a Scott? How it started out was 2.5 years ago, I accidentally created a cathode with lots of gold crud on it. And it ruined my other experiment, but In desperation, I reached in my tool drawer and pulled out this particular laser pointer. It's 1 milliwatt of power, and as the diagram shows, I shined it on the cathode, and some amazing things happened. 75 grams of water in the cathode increased in temperature by about 3.5 degrees, which is totally unexpected, and stayed there as long as I had the cathode on that particular, or the laser on that particular part of the cathode. If I moved the pointer just a little bit and get into a dead area, the temperature would drop off to a lower level, which indicates, as Ed said, there are active sites there that are more energetic and active than others. A lot of what I'm going to tell you today is either going to be wrong or nearly wrong, or I really don't know what's going on, but I've got some ideas, and with the help of guys like Scott, Chubb, and Peter, and some other smart folks, we may be able to figure this out if we can make it repeat. This is pretty highly repeatable if you follow some protocol. Not a lot of magic to it, kind of standard stuff. There are 6 things you have to do pretty well in order to see it. The first one is you got to follow a silly 17-step manufacturing process, or so it seems, to make a cathode that will then trigger the laser. You have to load the cathode with low current for a long time, 5 or 6 days usually, for the typical size you see on the screen. Then after you do that, you run it at a high current for 2 days, let's say, at an amp, amp and a half, and keep the cell over 50 or 55 C. And then when you get that done, you overplate the, I'm going to put this back on because I got ahead of myself. You use this little piece down here at number 9, which is a gold anode, a secondary anode. You hook that up to your power supply then and overplate a very small layer of gold on the cathode. And if you've stuffed enough hydrogen in the cathode and got that gold-plated layer over it, you're then ready to take the 5th step, and you can irradiate it with a predetermined wavelength. I got lucky. This happened to be one of the predetermined wavelengths that I've used. Peter thinks I'm all wet on the way I'm doing it, and I probably am because he's a pretty smart guy. But it seems to be correct. It's just probably not right for the reasons that I think it is. And I'm going to tell you the wrong reasons because that's all I know, and I'll let Peter correct any problems in the near future. He's good at doing that in a nice way. Another thing we discovered, it was quite by accident also, Cravens, Dennis Cravens up here really observed this. I had made a nice little box. I used to do this out on the bench, and of course everybody complained your calorimetry is lousy. So I built a silly little box around the cell, which I'll show you, and put this piece of Lexan into my window and shine a laser through it, and nothing happened. I'm so sick. I said, you do the least little improvement in your calorimetry and your effect goes away, so the skeptics are right. So instead of giving up, I popped the window out, shined the laser back through without going through this thing, and it worked. So I called Cravens and complained and whined, and he said, just put this in front of the beam while you're running it and see what happens. This takes away only about 1 millimeter of power, or milliwatt, sorry, of power out of the laser beam, and yet it effectively will kill the cell just like that. It just decline. I, at first, couldn't imagine why they'd do that, and Cravens said, well, think of polarization effects. You have external magnetic magnets on each side of the cell, which I forgot to talk about. We found that if you change the polarization, instead, if you have the polarization of the laser being vertical, for some reason, it evolves heat. If you put it horizontal, parallel to the magnetic field lines, the darn effect goes away. And I'll show you a graph of that in a minute. So if you do all those things, 6 things right, including being careful of what you send the laser beam through. You can't send it through certain things like plastic because it screws with the polarization for some reason and kills it all. Then you will see generally a heat effect. Now I have not been very successful, as a couple of you know, in trying to get others to get this done, but we're still working on that. I can do it reasonably well. But I haven't been successful with some guys in California, and most recently with Ed, but I think we will try eventually. Next 3 slides are just a 17-step procedure, and I'm going to skip that. I'm running out of time. Basically, you anneal, polish, and anneal, and re-polish, and re-anneal over about 4 steps, and I'll show anybody, I'll give you any of the data on how to do that. A piece of palladium, and when you get through those 17 steps, then you're ready to load, and everything works fine. If you do all that, and put it in, this is a real cell running, very similar to the one you have floating around the room. You'll see the gold there being plated over to the cathode, and when it gets nice and crusty, that's the time you know that it's ready to put the laser on. When the cathode gets kind of brown and nasty looking, it's time to blast it with the laser. And very typical cell, platinum anode wrapped around a small palladium cathode being electrolyzed. Same picture, but just with the laser being put on it, looks kind of neat. It radiates a very tiny portion of about 2 millimeter diameter. And from that, I've seen as much as 1 watt of apparent excess power coming out of that cell. And in fact, this very next graphic shows what happened. And I'll be glad to tell you afterwards how I compute excess power. It's basically compared the surrounding temperature to the cell temperature changes. It made about 300 milliwatts of excess power. I shut the laser off about 0.151 along in there, and boom, down comes the temperature again. So it seems to be related to the presence of the laser. About a half a degree increase in 75 grams of water. Take a shot glass and fill it full of your favorite beverage and shine one of these little laser pointers on it and get a Radio Shack and see if you can make it go up a half degree. 2 minutes? Okay. Just another example real quick. This is a year later, year and a half later, the same effect appeared. Laser on, up it goes, 600 milliwatts. October 11, October 12, 2002. Now we talk about the model, what I think is going on. And again, take this with a large amount of salt. It may be untrue. I think the hydrogen is trapped in a little lattice cavity, kind of like a quantum well, which you can resonate with a laser if you pick the right frequency compared to the temperature of the cell. And this is a two-dimensional quantum particle in the box type deal. And it so happens that two of the resonant wavelengths that would couple with this little cavity, with the hydrogen in that cavity, as computed with some mumbo jumbo, which I'm going to skip. It's just particle in the box. Go look it up. Here's a laser pointer optical spectrum that I made a year after I did it of this particular laser pointer, and it's centered around 668 nanometers, which is exactly one of the computed wavelengths if you follow my little mumbo jumbo. The other one, the other one is laser pointer 2, which is this laser centered at 655, exactly on resonance. And when I radiated them, I get 3.5 degrees increase in the cell temperature. How much time do I have? Let's go.
30 seconds. But actually, we have time for questions.
Okay. I'm going to end. Let's skip a bunch of slides. And essentially, the theme of my talk here was that the effect has persisted from tabletop calorimetry to pretty good calorimetry. And I will even put up another slide on this. Thank you very much, and take any questions.
Yes, go ahead. What's your question?
Let's see. Initially, you commented that your friends in California, I think, aren't saying that they're not saying anything. But the question is, what's the ratio of the response compared to the absorbed laser input in the experiments?
Good question. I'm glad you asked it now because I left it out. The first round of lasers were 1 milliwatt apiece, and I saw up to a 600 or 700 milliwatt signal as a result of that triggering. So it's a very large ratio.
How much of your light is absorbed?
Pardon?
How much of your light is absorbed?
I measure in and out, and the reflection I lose about, say, a 30 milliwatt signal, which I do now, 35 or so. I end up getting 30 out of 35 milliwatts actually reflected. So when you get the golden dark red on, you don't lose much.
Back there? Yeah.
Anybody?
The slide that you had for current electrodes mentioned that you did it with a magnetic field.
Right. How strong? Good question. For heat of the moment, I forgot to tell you. I heard 350, 400 gauss is about right.
No, go.
Gauss? No, gauss.
Gauss? Okay, large. Yes.
I'm curious, are you operating this in constant voltage mode? How are you getting your power? Do you see any change in current?
LabVIEW is controlling it now in constant power mode, and I'm allowing LabVIEW to twiddle the amperage to keep the power at 7 watts. And typically what happens when the effect kicks on and the electrolytic cell warms up, you see a decline in cell resistance, of course, and it then causes, you have to twiddle the amperage to keep the power the same. The way I ran most of these was in constant current mode. And so then voltage would drop as you kicked off and warmed up the electrolyte.
I have a question. What was your percentage success rate? Do they always work, or?
Most always work if you make the cathode right. I had, in 2002, I did, something like, what was it, 20 experiments or so. I had 3 out of 3 worked when I made the cathode exactly right, and 6 out of 16, I think the numbers are right, work if I sort of made it right.
What is it? Actually,
Input. Are we rebooting?
Trying.
I'm good. We practiced that.
Took a minute too.
I'll give you extra time. I'll get it, don't worry.
What are we doing? Did anyone get the structure of the palladium of the Chubb loading? Whether you can see the, for example,
I'm sorry, what are you asking, Dennis?
well, anyone who has things.
What was the question?
Whether you looked at the structure itself of
That is different.
George
There's been a lot of optics in this study.
whether the studies
That's video.
Well, it goes into the optical sense, predominantly. But they're very...
And for the H2 plus molecule,
Push record.
you can see the dark line is the exact, the frost and mucilin is pretty close to it. It's better than the Morse potential. And if you use this potential, you can understand the calculations of Kuhnen and Nauenberg to within factors of a DD fusion rate on the order of 10 to the minus 65 seconds per molecule. Basic idea is that the molecular result is what I would expect in a metal deuteride. Iwamura has proposed that you can have screening in the metal deuteride, which gives you much larger tunneling rate. KP Sinha and I cooked up a linear response model for the dielectric response between 2 deuterides in a metal deuteride. And the conclusion is that the screening at 100 Fermi distances, very small distances, is no different than from the molecular case. And this is consistent with low energy DD fusion cross-section measurements in titanium deuteride at Kasagi. We went down to about a kilovolt and got the same screening values as for molecular deuterium. I've been trying to understand how things work from a theoretical point of view. And DD fusion reactions in vacuum are normally described using, or were described for many years using resonating group method. The idea is you make a trial wave function that has nuclear pieces and free channels which tell how far apart the nuclei are. And you optimize the free channel factors variationally given your nuclear basis being fixed. I generalize this to the case of the lattice. I use the same nuclear factors, and instead of having just the center mass of the nucleons involved in the free channel factors, I've included the rest of the lattice. And the optimization formula is very similar to the resonating group method. What this does is allows description of photon exchange. The reason photon exchange might be important is because there's experiments that appear not to be explainable by normal vacuum physics. The first one of which came to my attention was the experiment of George Chambers. Deuterides came in from an ECR source at about 500 electron volts, hit a palladium deuteride foil, and very low rate, alphas in the range of 18 to 21 MeV came out. So the question is how to explain that, because there are no low energy DD fusion reactions which give such energetic alphas as product. And after a few years of thinking about it, the proposal was 2 deuterons make helium-4. The selection rules are satisfied with photon exchange. Photons are exchanged with photon mode, and the palladium nucleus somewhere else disintegrates, kicking off an alpha. The predictions based on going to the ground state of the resulting product molecule are between a little bit more than 18 and 21 MeV. If I include it to excited states, it comes down a little bit and provides a reasonably good match to Chambers' experiment. Basic idea is that you have 2 deuterons at one side, they'll fuse, exchange phonons with a lattice. And the phonons will encompass the region, including the site where the 2 deuterons are, plus the site at which another nucleus is, exchange of phonon here. Second order reaction for energy balance, the energy from the reaction here is expressed elsewhere. That's the significance of Chambers' experiment. Similar conclusions obtained by looking at Cecil's result. I think Lipson, who's here, has seen some fast alphas as well in at least 2 experiments. If such reactions occur, then you should look at all possible site-other site interactions and reactions. And the density of states is going to be largest if you've got a resonant reaction of the discrete final state. Such a reaction is 2 deuterons making helium-4 at one site, exchanging energy, or exchanging phonons with a photon field, and then having helium-4 make 2 deuterons somewhere else. I call it the null reaction because on the one side balanced exactly by the other side, 2 deuterons and helium-4 just seem to change places. No energy, or little energy, gets exchanged here. Now by itself, we thought for a long time that this reaction, even though it's theoretically predicted to have the highest rate, would not be observable, because there's no way to tell whether 2 guys are changing places. But after a while, it occurred to us that the 2 deuterons formed from the dissociation helium-4 have to tunnel to get apart, and the tunneling is inhibited by the Coulomb barrier. So in principle, this is observable by having a particle coming in and hitting 2 deuterons at the same time. Kasagi was looking at 100 keV deuteron beams of titanium deuterate, and he saw fast protons, fast alphas. The signals included a very broad background, and this is a proton channel. And there's primary reactions, there's secondary reactions. The secondary reaction would give fast protons and fast alphas. But you can calculate deuteron hitting helium-3 gives a spectrum this wide. Helium-3 from a DD reaction hitting another deuteron gives a spectrum this wide. But a 3D reaction, a deuteron hitting 2 deuterons close together for the measurement of these localized states would give a signal that's very broad. And if you look at the data, this is for the secondary thing, this is the very broad thing. This has been observed at other laboratories in Japan, China, and we've seen in the last year and a half at Naval Research Laboratory. A couple of channel equations for the lattice resonating group theory set it up in detail for the 2-site case and demonstrated exchange of excitation. The resulting equation, an infinite order Brion, Wigner Brillat theory, looks like the molecular problem of an exchange problem of low radius. You can solve it in 1D, you get localized states. You can solve the radial case, and the radial case gives a substantial modification of the probability amplitude of low and small radius. So the proposal here is that this mechanism, this phonon exchange, excitation exchange mechanism, in fact, can change the tunneling probabilities between deuterons and non-deuteron.
Okay, question? Yeah.
Channeling effect where you're moving off axis, not a channel, but you have a channel effect.
Let's see.
Can you stand up? Oh, I'm sorry.
Let's see that the.
Repeat the question.
I think I understand the question. The calculations I'm doing here start out with a molecular state, molecular deuteron configuration of the molecule. and they come in the metal, and they come together.
the 100 kV deuterons coming through.
Right, there's no evidence for any channeling effects in those experiments. Hubler at NRL looked at that and changed the target angle and changed the morphology on the surface. There was no dependence of this effect on any channeling factor.
Sure.
In Lipson's recent work, I think you'll report, in addition to 16, it may be alpha particles and C is 1.5, so it may be protons coming out. Do any of these predict protons that
Normal diffusion protons, if they go through stuff, will of course slow down. Protons in palladium and in titanium tend to come out with significantly higher energy. Cecil's experiments saw protons up 11 MeV, which matches this mechanism, which would give 12 MeV protons. It's a rather good match there. So it's much slower protons we'll have to talk about.
I'm sure we're going to have to cut it off, but I very quickly. Have you checked your deuteron wave functions for use of the photo dissociation of helium? Yes. Good. I'm sorry. Let's see. Okay. Okay, moving on here. We now have a talk by Dr. James Cravens from Professor Cravens from Eastern New Mexico University. The title of the talk is Heat Recovery from Exploding Structured Deuterated Wires. And I give you Professor Cravens.
Got about half people that I don't know. The rest of you I know. I have been working on cold fusion things, electrolytic cells, typical ponds and plasmin, and doing that sort of stuff. I just recently, last 6 months, went to exploding wires, and this is more like hot fusion. I apologize, but that's the way it works. I was doing pulse things and laying down co-deposits of weird stuff. The reason why I did this is I got tired of the calorimetry. Yes.
In your abstract, you said imploding in there. Was that
right? It is actually imploding.
Oh.
I use exploding when it's actually imploding. We'll get to that. Basically, I take wires and load them up. These wires are about 30 gauge, 0.127 millimeters, 5/1000 of an inch, whatever your units are. I take the wires of palladium, I electrolytically load them, I etch them with nitric acid, formic acid, then I electrolytically load it like a typical cell. These wires are roughly 1/2 centimeter long. By the time they're on the device, 2 silver rods, the active length is about 1/4 centimeter. I then gold plate it. I gold plate with the type of things that you cover Lexus decals on the cars, typical gold paint type stuff. It's electrolytically on here. In a minute I'll tell you why. They have done a lot of exploding wires in the past, but nobody seems to layer them. I think I have 2 or 3 people out there that are familiar with hydrogen bomb designs. Basically, this is called a tamper or a pusher. You want something to contain your material, particularly the X-ray, so you don't have energy losses, because most of your energy loss is through the X-ray spectrum. And also the radiation pressure does things for you. So basically, I've got a high-density deuterium source with a tamper around it, and I will be putting energy through this, and it will flow from the inside out, where most hot fusion people have all these little Z pinches with wires around it and trying to use radiation pressure on a plasma. My plasma is actually produced right in the material itself, so there's less expansion losses. If you know much about hydrogen bombs, you've got a uranium source, and I'm talking about the old ID type things, first ones. They explode